Hello, in this video we're going to finish off Newton's laws with his third law. You've probably heard this one stated before. You probably heard it as for every action there's an equal and opposite reaction. Action is an archaic name for force. So the way we're going to write this is the force of object 1 on object 2 is equal and opposite to the force of object 2 on object 1. Opposite here means opposite direction, since after all forces are vectors. And that's Newton's third law. Okay, so let's look at a sketch of this. So suppose we had a block sitting at the edge of this ramp here, and then a ball rolls down the ramp and bumps into the block. Okay, and the two are pushing on each other. We call the block object, or the ball object 1, the block object 2. Then right here where they're touching each other, there are two forces. A force from object 1 acting on object 2, and a force from object 2 acting on object 1. And Newton's third law tells us that those two vectors have the same magnitude and point in exactly the opposite direction. And this is true for pushing and pulling and any kind of force. The objects don't even have to be touching each other. So there's a force between Earth and the moon. That's gravity. This is not to scale, by the way. If this was to scale, the moon would be 30 Earth radii away, so it would be way, way, way off the right side of the slide. Anyway, I point that out because I'm actually an astronomer, so that kind of thing is cool to me. Anyway, so the force from one is equal and opposite to the force from the other. In this case, we'd say the Earth is object 1 and the moon was object 2. All right, and a better way to describe this is really to say that a force is an interaction. The reason there's always these equal and opposite pairs is because it's part of an interaction. Two objects have to interact for there to be a force. So, instead of saying, for example, that I push on the computer and the computer pushes back on me as if those were separate things, it'd be more accurate to say I force the computer and the computer forces me. So that would be, it's not how we say it, but that would be a better way to say it. Now, one thing to be careful about is equal and opposite force pairs doesn't mean that two forces just happen to be equal and opposite. It's the two forces are part of the same interaction. So let's say we have a block sitting on a table. Say the block is object 1, the table is object 2. At the point of contact, there's an interaction where we have equal and opposite forces. Both of those are normal forces. So we have a force from the block on the table and a force from the table on the block, and both are the table and the block being solids and not passing through each other. They're both normal forces. Be careful, this is not the same as the situation where we've got a block sitting on a table and we draw the forces acting on the block. We draw a free body diagram for the block and we say that there's a normal force and then there's the weight, and they're equal to each other in opposite directions. No. That is not the same thing as Newton's third law. While it's true that a block sitting on the table has a weight that's equal in magnitude to the normal force, it's not because they're equal and opposite force pairs. It's because the net force on this block is 0, and the only way that could happen is if the up force was equal in magnitude to the down force. So they're not part of the same interaction. Now, you might argue that that's semantics, but being able to tell the difference is a nice conceptual clarification, recognizing what is an equal and opposite pair because it has to be versus coincidence. Okay, see you in the next video.